Hi, I'm Petra Wolf from the University of Trier, giving a talk about synchronization of deterministic visibly pushdown automata, which is a joint work together with Henning Fernau. So what we're going to do in this talk is we're going to generalize the concept of synchronizing an automaton to the more general class of deterministic visibly pushdown automata. So the models appearing in this talk are the following. The most general automaton we will consider is a deterministic real-time pushdown automaton, where the real-time condition forbids for epsilon transitions. Then we will also consider counter automata, where a pushdown automaton is considered a counter automaton if we only have one symbol we can put on the stack, so we can basically only count with the stack in unary. Then the main class of automata in this talk will be visibly pushdown automata and the subclasses thereof, considering very visibly pushdown automata and visibly counter automata. How these classes are defined will be discussed in a few moments, and we also considered final turn variants of all of these classes of automata. So what is actually a visibly pushdown automaton? Well, for visibly pushdown automata, we can partition the input alphabet into three distinct sets. The first containing all call letters, with which we can put a single symbol on the stack. Then next, it is a set of internal letters with whom we do not consider the stack at all. So these are basically transitions in a sense of a finite automaton. And the set of return letters, where with every return letter we read a symbol from the stack and also remove it thereby. The only exception is that if we read the bottom of stack symbol, so if there are no symbols left on the stack, then we will simply observe that we encountered the bottom of stack symbol and will not remove it. So hence, for visibly pushdown automaton, the height of the stack is predetermined by the input word and therefore independent of the current state. So means that if we read the call letter and we actually put something on the stack, then we will put a single symbol on the stack. In the even more restricted class of very visibly pushdown automata, not only the stack height is predetermined by the input word, but also the actual stack content itself is predetermined by the input word and hence independent of the current state. So for very visibly pushdown automata, we will not only have that we put a single letter on the stack regardless on where we read the call letter, but we will also put the precise same letter on the stack regardless on where we read the actual input letter. So now we want to lift the concept of synchronization to the class of visibly pushdown automata and therefore recall what synchronization actually meant for finite automata. We call the finite automaton synchronizing if there exists a synchronizing word that maps all states of the automaton to one single state. And the complexity of this problem is if we only ask whether the automaton is synchronizing at all, meaning whether there exists a synchronizing word, then this problem can be solved in polynomial time. Whereas if we put any restriction on the synchronizing word, such as we demand that the synchronizing word has a length up to some threshold, then this problem becomes NP-complete. And if we relax the condition that we want to map all states of the automaton to one state and instead demand that only a given subset of states is synchronized into one single state, or on the other hand, that we ask whether we can map the whole set of states into a subset instead of a single state, then these variants become p-space complete. So now how do we generalize this concept for pushdown automata? We already found a generalization for general PDAs presented at MFCS this year, where we defined the problem as follows. Well, first of all, we want to keep the condition that a synchronizing word needs to map all states of the automaton to one single state. But since we are considering pushdown automata, with every run, we also have a stack hanging around, and we somehow have to talk about how this stack should behave in terms of synchronization. And one option would be to demand that after reading a synchronizing word, all stacks should be empty. Or we could say that we interpret synchronization in terms that the stack contents should be identical on all runs. So they don't need to be empty, but they must contain the same word. Or we could also argue that we don't care about the stacks at all and that we just want to synchronize the state set, and hence we allow the stack contents to be arbitrary. So the actual problem we're considering is the following. We're defining the synchronization problem for pushdown automata in one of these stack models, as we're given an input PDA and we want to know whether there exists a synchronizing word in the respective stack model. And we can also define this problem for all of the introduced subclasses of pushdown automata. So what we actually have, we're starting in all states in parallel, and we want to read a synchronizing word such that after reading the word we end up in one single state. And now with every run induced by the synchronizing word W, there is a stack associated with this run. So if we're considering the runs in parallel, we have a bunch of stacks which can have different contents. But if we are considering one single run, then we always will have only one stack. So we are in a single stack model. We are demanding in the empty stack model that after reading the input word W, all of the stack contents are empty. So there is no letter on the stack left except for the bottom of stack symbol. In the same stack model, we demand that all of these stacks have the same content in the end. And in the arbitrary stack model, we allow them to have simply an arbitrary content. And we observed in the general case of general pushdown automata that this problem is undecidable in all three stack models. And it is still undecidable if we restrict our model to general counter automata. So now, how does this picture change if we actually consider visibly pushdown automata, which share some nice property with finite automata? And it turns out that here we can also observe a similarity to finite automata in the empty stack model, meaning that in the empty stack model, we can solve the synchronization problem for deterministic visibly pushdown automata in polynomial time, as in the case for finite automata. But if we consider the other stack models, such as the same stack model and the arbitrary stack model, then this problem is harder, but it is still a remarkable drop in the complexity from undecidability in the general case. If we consider even more restricted subclasses, such as very visibly pushdown automata, then this problem of synchronization is actually solvable in polynomial time in all three stack models. And this is also the case for visibly counter automata. So now let's start with considering some proof and begin with the empty stack model. In the empty stack model, the question whether a given deterministic visibly pushdown automaton can be synchronized is solvable in polynomial time. And to prove this, let's make a case distinction on whether we do actually have symbols which can read the stack or if we don't have them. In a case that we do not have any symbol which can read the stack, meaning that the set of return letters is empty, then as we want to synchronize in the empty stack model, meaning that after reading W, our stack should be empty, we cannot put anything on the stack at all. So meaning that we cannot use any call letter at all. And therefore, the problem basically boils down to DFA synchronization, as we can only use internal letters. On the other hand, if we do have return letters, meaning that if we have some letter defined on all states which can read the stack and remove symbols from the stack, then we can apply a pair argument similar to the one for finite automaton, in the sense that our input visibly pushdown automaton can be synchronized in the empty stack model if and only if all pairs of states can be synchronized also in the empty stack model. And I want to stress out that these pair also need to be synchronized in the empty stack model, meaning that after applying a word which synchronizes this pair, the stack should be empty again. And then the algorithm works as follows. We start in the whole set of states, pick two states at random, apply a word which synchronizes these two states in the empty stack model, and then again pick two remaining active states at random and apply a word synchronizing them, and so on. And the reason we can do this, meaning that the reason we can combine these words synchronizing pairs of states, is that since we are considering visibly pushdown automaton, the stack height on all runs is equal if they read the same input word. And therefore, if we are focusing on two runs and we notice that at some point the stacks for these two runs are empty, then we know that also the stacks of all other runs which read the same input word will be also empty. Meaning that after we have synchronized a pair in the empty stack model and the stacks of these two runs are empty, we know that all other stacks are empty as well, and we basically are back in the initial situation with respect to the stack content, and we can again apply a word which merges another pair of states starting with an empty stack. And in order to determine for a pair of states whether we can synchronize this pair, we can simply look at the pair automaton of our input visibly pushdown automaton, which is again a visibly pushdown automaton since our stack height is equal on all runs, and therefore if we're simulating the run on one state in the first entry of a pair and the run on the second state in the second entry of the pair, then when we consider their stacks, the height of these two stacks will be the same and cannot differ by an arbitrary amount of height as in the general case, and therefore we can also simply pair the stack alphabet and again obtain a single stack, meaning that this pair automaton is also a visibly pushdown automaton, for which we can test in polynomial time whether it accepts a word at all. Now, the next line of results considered the more restricted class of very visibly pushdown automaton, where the very visibly condition ensured that regardless on where we start reading an input word, the stack contents will be identical at any time. And since this already gives us that the stack contents after the synchronization are identical, we already have that the arbitrary model is equivalent to the same stack model for this class of very visibly pushdown automaton. And these two models are also equivalent to the empty stack model by the following observation. That is, if our set of return letters is empty, so if we do not have any symbol which can read the stack, then also our transitions cannot depend on the content of the stack at any time. So the stack is basically a write-only tape, and therefore we can also simply ignore it and reassign all call letters as internal letters. On the other hand, if we do actually have return letters, meaning if this set of return letters is non-empty, and hence we have some symbol which can empty the stack and is defined on any state, we can simply empty the stack after synchronizing first all states, since as our stack contents are identical, the different runs are no longer distinguishable after synchronization because they are all in the same state and they all have the same stack content, and hence we can simply erase the stack and we will not cause these runs to split again. Now let's focus on the two remaining entries of this table. So now let's consider the class of visibly pushdown automata in the same stack model. And we have that here the synchronization problem is p-space hard. And we can show this by a reduction from the p-space complete problem of synchronizing DFA into a given subset of states. So the task is here we are given an automaton A and a subset of states, and we want to know whether there exists a synchronizing word that maps all states of the automaton into the subset S. And the construction now works as follows. We add an additional state, which will be our single synchronizing state, and we add a new call letter A, with which we map to this synchronizing state from all states of our automaton in a way that we protocol on the stack whether we came from a state in S or from a state outside of S. And for the synchronizing state, which is the single synchronizing state as we define it as a trap state, meaning that we stay in the state for every input letter. For this state, we define that the call letter A adds a happy face on the stack. And since this state is active the whole time, and we have to read the letter A at some point in order to read the state from our initial automaton, we will have a run which protocols a happy face on the stack. And in order to be able to synchronize in the same stack model, we must make sure that all other runs also only put happy faces on their stack, as we do not have any letter which can remove letters from the stack. And therefore, we must make sure that before we read the letter A, we have first mapped all states of the automaton A into the subset S, such that when we read the letter A, we will only add happy faces to the stack and can happily synchronize all runs. And now the observation here is that we did not have any letter which can actually read the stack, meaning that the set of return letters is empty, and hence this construction also works for the variant of this problem where we define that the input automaton must have an empty set of return letters indicated by the suffix no return. If instead we have the promise that we will have a return letter defined for all states, in this case the problem becomes solvable in polynomial time by a reduction to the synchronization variant in the empty stack model simply by the identity function, because if we can synchronize our input automaton in the same stack model, then we end up in a configuration where every run is in the same state and has the same stack content on each run. And as we already argued in the very visibly case, these runs then are no longer distinguishable, and we can simply empty the stack in the end. And the other direction is trivial, since if we can synchronize the automaton in the empty stack model, then after reading the synchronizing word, all stacks are empty, and especially they will have the same content, namely none. So now look at how the picture looks if we relax the conditions on the stack even further, in a sense that we now allow an arbitrary stack content after synchronizing the state set. And again, here the problem is p-space hard, but here we only have p-space hardness so far. So we do not have matching upper bounds as in the other cases, and this is actually an interesting open problem to find the precise complexity of this problem in general for the arbitrary stack model. And we actually proved this by reduction from the p-space complete problem of synchronizing from a given subset with respect to a DFA, meaning that we are given a DFA and a subset of states, and we now want to know whether we can synchronize all states in the subset, meaning that if we start in a configuration where only precisely the set S is active, can we proceed with reading a synchronizing word such that we end up in one single state for all runs. And the construction works as follows. This time we assign all letters of the initial automaton as call letters and not as internal letters as before, such that whenever we read a letter from the initial automaton, we protocol the state from which we read this letter on the stack and proceed with the active state as we did for the initial automaton. Then we further add a single return letter R, which can read the content of the stack in a way that we undo the transition we've previously protocoled on the stack. Meaning that when we read with the letter R a symbol Q from the stack, then we map to the state Q. And if there is no state protocoled on the stack, meaning that if we can see the bottom of stack symbol, then we use the letter R to map into the set S. Meaning that especially if we read the letter R as the first symbol from the configuration where all states are active, then we end up in a configuration where precisely the set S is active, and we further cannot use the letter R to cheat in a sense that we first merge some state and then map into S such that not the whole set S is active. This is not possible, since then if we merge some states, then we have already used some letters from A in order to merge these states. And therefore we protocoled some visited states on the stack. And if we then would read the letter R in order to try to map into S, instead we would undo the previously taken transitions until we end up in the initial situation again, from which we can only map to the set of states S. As an observation, here we had explicit return letter R, meaning that the set of return letters was non-empty for all input DFAs, which gives us that this construction also works for the return variant of the problem and gives us that this problem is p-space hard. Remember that in the same stack model, for this variant, we had solvability in polynomial time. So now let's consider the last missing case here, meaning that how does the problem behaves if we have no return letter in hand. So if we restrict our problem to input visibly pushdown automata with an empty set of return letters, then it turns out that for the arbitrary stack model, this problem is solvable in polynomial time by the following argument. Since we cannot read the stack at all, and we further have no restriction on the content of the stacks after synchronization, the stacks are basically just a throwaway garbage tape, and we could simply also ignore it and throw it away, in a sense that we reassign the call letters as internal letters and simply end up with a DFA. So to summarize the results we've seen so far, when we distinguish between the no return variant, where we do not have a return letter, and the return variant, where we have the promise that we will have a return letter, then the same stack model and the arbitrary stack model behaved complementary. And this is interesting, since in the previously considered class of general pushdown automata without visibility, we could not observe a difference here. So there these two stack models behaved just the same. And now for visibly pushed-down automata, we could actually observe a difference in the complexity of these two stack models. And as mentioned earlier, for the arbitrary stack model, we only have p-space hardness, and we do not have containment in p-space. And the precise complexity of this problem is still an interesting open problem. And in the paper, we have further considered final turn variants of these classes of automaton, where we restrict the number of times the stack height behavior can change from increasing to decreasing and increasing again. And while in a general case of general PDAs, we observed a drop in complexity for this variant, here for visibly pushed-down automata, we actually observed a rise in the complexity. And so far, I want to thank you for listening and hope to see you in the Q&A session.